A customer's container exploited dirty pipe to overwrite the hosts etc/passwd, gaining root access and installing a cryptominer that accessed every tenant's file system. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Docker V's virtual machine. Containerization packages an app with its dependencies into a container that shares the host kernel. Unlike VMs, which need a full guest OS per instance, containers strip away that overhead. You get near-native performance, instant startup, and higher density. But the trade-off is real shared kernel means weaker isolation. A VM runs a full guest OS on top of a hypervisor. Each VM has its own kernel, memory, and device drivers. VMs provide stronger isolation because a kernel exploit in one VM does not affect others. But they are heavier, minutes to start, and gigabytes of RAM overhead. The fundamental difference is where the isolation boundary sits. VMs isolate at the hardware level. Each VM runs its own kernel. Containers isolate at the OS level. All containers share the host kernel. This single difference cascades into every other trade-off. Here we run two different containers and check their kernel versions. Both show the same host kernel version, proving they share the host kernel. This is the core mechanic. Containers are lightweight because they don't duplicate the OS. Performance differences are context-dependent. Containers deliver near-native CPU performance within 1–2% of bare metal. VMs add 5–15% overhead. The biggest gap is disk I/O. Containers using bind mounts are near-native, while VMs using emulated drivers can be 30–50% slower. We run Sysbench CPU benchmark inside a container. The events per second metric shows near-native performance. Compare this with a VM to see the overhead. Security isolation is the most important trade-off. VMs have a separate kernel per instance. A kernel vulnerability in one VM does not affect others. Containers share the host kernel. A kernel CVE affects every container on the host. Mitigations like Seccomp and AppArmor are defense in depth, not a separate kernel. We inspect a container's security options. The Seccomp profile filters syscalls. Running as root inside a container is bad practice. Always use a non-root user in production. Operationally, containers scale in seconds and are 1050x denser than VMs. Patching a container is a single image rebuild. However, VMs provide a full OS environment for debugging, which containers lack. Scaling containers is fast. This command scales an API service to 10 replicas, all ready in seconds. VMs would take minutes. The VM versus container debate is not binary. gvisor provides a user space kernel that intercepts syscalls. Kata Containers runs each container in a lightweight VM. Firecracker starts a micro VM in 125 ms. Choose based on your security requirements and performance budget. Running a container with gvisor runtime. The container's kernel info shows gvisor instead of the host kernel, indicating syscalls are intercepted. VMs provision a full disk image per instance, typically gigabytes. Docker layers images using copy-on-write, sharing base layers across containers. This means a team running 50 microservices might consume 2 GB of unique storage versus 500 GB of VM sprawl. Here's a side-by-side comparison. A VM uses a 20 GB disk image and takes 45 seconds to boot. Docker uses layered storage totaling 172 MB and starts in 120 ms. Docker wins on storage efficiency and startup speed. Docker images bundle dependencies but still rely on the host kernel. If your container uses a syscall not supported by the host kernel, your app crashes. VMs don't have this problem, they ship their own kernel. Test containers on the target kernel before production. This Docker Compose snippet adds a deployment constraint requiring the host kernel to be at least 5.15. This ensures the container's syscall requirements are met. Docker tags are not versions. Latest can be overwritten and break production. Mutable tags destroy reproducibility. Always pin by digest or use git commit hash as tag. This is how you pin a container image by its digest. The SHA-256 hash guarantees you get the exact same image every time, eliminating drift. This is the same issue we highlighted at the start. Here's exactly why that happened. A team ran untrusted user code in Docker on a shared Kubernetes node. A kernel CVE 2022-492, allowed the container to escape via cgroup release agent. The symptom: all pods on that node suddenly showed root processes from other tenants. The root cause: the shared kernel allowed a single exploit to compromise every container. The fix is to never run untrusted workloads in standard containers without a VM boundary. Use Kata containers or gvisor for enhanced isolation. Running with runtime equals runsk provides a user space kernel that intercepts syscalls, preventing escape. This limits the blast radius to a single tenant. Running containers as root is a security risk. If a container escapes, the attacker gains root access on the host. Always use a non-root user in production. Without memory limits, a single container can consume all host memory and trigger OOM kills on other containers. Always set memory on every production container. Using latest as a tag is dangerous. The base image maintainer can push an update that breaks your application. Always pin by digest or use a specific version tag. The article mentions kernel CVEs like dirty pipe, but doesn't emphasize that a single container escape can compromise all containers on the host because they share the same kernel. In contrast, a VM escape is extremely rare and typically requires a hypervisor vulnerability. This is the core security difference. Containers have a single point of failure at the kernel level, while VMs isolate each tenant's kernel. The article discusses namespaces but doesn't show how to inspect them. Use LSNS to list all namespaces on the host and see which processes share which namespaces. This helps debug isolation issues and confirms that containers share the kernel but have separate namespaces. The article mentions Seccomp but doesn't warn that the default Docker Seccomp profile allows many syscalls that could be dangerous. For production, you should create a custom Seccomp profile that only allows syscalls your application needs. Use strace to identify required syscalls and generate a minimal profile. This reduces the attack surface significantly. To diagnose container issues, start by checking the host kernel version. Use Docker Inspect to see security options. Monitor resource usage with Docker stats. Use strace to check syscall compatibility. Let's run through some common interview questions. What is the main difference between VMs and containers? VMs virtualize hardware with separate kernels. Containers share host kernel via namespaces. How does a kernel CVE affect containers versus VMs? In containers, one CVE compromises all containers on host. In VMs, only the affected VM. What is gvisor and when would you use it? A user space kernel that intercepts syscalls. Use for moderate security multi-tenant workloads. And a few frequently asked questions. Are containers secure? They can be with proper configuration, Seccomp, AppArmor, non-root, but they don't provide VM-level isolation. Which is faster, containers or VMs? Containers start in milliseconds versus minutes for VMs. CPU performance is near native for both, but VMs have 5–15% overhead. Can I run Windows containers on Linux? No, containers share the host kernel. You need a VM or WSL2 for cross-platform. To sum up, VMs provide strong isolation with separate kernels, while containers offer density and speed by sharing the host kernel. Choose based on your trust boundary. For untrusted code, use VMs or hybrid approaches like Kata containers. For your own services, containers are efficient and fast. Ready to go deeper? Up next, how Docker works internally, then Docker architecture explained, then Docker images and containers. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.